Hello everybody again. Well, today we're going to talk about exponential functions, okay? And this is important because it's a way of describing how things change. So everything that we have been talking about so far has been linear or quadratic, okay? And if I look at a linear change, it's going to be this constant change, okay? And no matter where I am in the graph, the change from one position to another is the same. When we talk about an exponential function, we're going to look at something that has a changing rate of change, okay? So notice as I go towards x, the linear stays the same, right? But this exponential is constantly getting steeper and steeper. My slope is increasing, right? If I look over here, my slope is decreasing, and it's going to be approaching the x-axis, and something we're going to learn is that an exponential function never intersects or touches the x-axis, okay? So a couple of characteristics here of exponential functions. They are always positive, okay? They never touch or reach, whatever words you want to use, the x-axis, okay? They're constantly changing, okay? And it just depends on which direction you're talking about, how they're changing. Here, as we're, x is going to infinity out here. Okay, we're moving to the right. This is going to get steeper and steeper. As x goes to minus infinity over here, it gets closer and closer to the x-axis. So we can say that the x-axis is an asymptote. It's a new word, something that is approached but never reached, okay? So we know when we're talking about a linear equation, we're looking at something that's y is equal to mx plus b, right? Well, what about this exponential function? Here we're going to look at y is equal to b to the x, okay? Now notice here, x, we're going to consider this our independent variable. It's the input. X here is an actual exponent, okay? And hence the word exponential. So my input is x. B here is my base. So let's say y is equal to b to the x. We're going to say b is my base, okay? And x here is the exponent. And notice now, whatever this base is, whether it's 1 or 2 or 3, it stays the same, but now x is going to be changing, right? As I'm moving to infinity, it's going to be to the first. It's going to be b squared, b cubed, b to the fourth. And that's why you see this increasing, constantly getting bigger and bigger, right? If you were thinking of b as 2, 2 to the first is 2. 2 squared is 4. 2 cubed, 8. 2 to the fourth, 16. So you've got this 2, 4, 8, 16, constantly getting bigger with each little change in x, okay? So something else we're going to add to our criteria for an exponential function, now that we have this formula, is that whatever this is, this point right here is the point 0, 1. And 0, 1 is on every single exponential function. Now, how can I say that? Well, here's x, right? X is my input. I'm talking about b to the 0. We know that anything to the 0 power is 1, and therefore y is always going to be 1. So doesn't matter if my base is some different number from one exponential function to another, it's always going to intersect this point 0, 1. Now, the other point that it's going to intersect is a point over here where we're talking about x is out at 1, all right? This here will always be the point 1, b, because again, we go back to our formula. If x is my input, I'm talking about b to the first power, right? So it's always going to have this point on the curve at whatever the base value is for y, okay? So these are two important features of an exponential function. It will always be intersecting at 0, 1, and it will always be on the point 1, b. Now, what I've talked about here is for an exponential function where my b value, okay, is greater than 1, okay? And it changes when b is less than 1. And I want to show you that one. So if I'm talking about b less than 1, okay, so let's say b is less than 1. So for example, let's look at 1/2, all right? So if I have my function is y is equal b to the x, and I'm going to say, so let's look at y is equal 1/2 to the x power. Well, what do we know? Well, at x is equal to 0, it's going to be on that point 0, 1, right? So let's just make our little graph here. So x is 0, y is going to be 1. Well, what if now x is 1, okay? Well, I plug that in, it's going to be 1/2, isn't it? So if this is 1, I'm going to have a point here. What if x is 2? 1/2 squared is 1/4. So I'm going to be here. Let's look at -1. When x is -1, we know a negative exponent means take the inverse of, right? So 1/2 to the -1 is going to be 2. Let's look at -2. Well, again, I'm going to flip it. So 1/2 flipped is 2. 2 squared is 4. So I'm going to be talking about this. So look what's happening here. When b is less than 1, and I'm going to add this to it, but greater than 0, okay, I'm going to get this opposite shape of what I had when b was greater than 1, okay? So, but it's still going to have the characteristics of going through 0, 1, We proved it went through 0, comma b, remember? I'm sorry, 1, comma b. It's constantly getting steeper as it's moving away from the x-axis here. On the opposite side of the y, it's still approaching the x-axis as an asymptote, but it's just kind of reversed from my b greater than 1, okay? So we're going to take that and we're going to use that to springboard into one other type of all this, and we're going to talk about the natural number, and it is written as a lowercase e. This is a value that becomes quite useful in growth and decay types of equations. It can be, radiation. It could be population. It just anything growth or decay oriented. Okay, and E is represented by the equation 1 plus 1 over n all to the nth power. So as n increases, we're giving ourselves more and more accuracy on this number. And what you're going to find out as n increases, we're going to get a value that looks like 2.718 continuing on, okay? So a real common exponential function is f of x is equal to e to the x, okay? Now notice e here is my base now. So it's still a number. It's just something that we use a representation for. And we want to use this representation and not some approximation. Because once we start doing that, we're going to start dealing with estimating errors or rounding errors or what have you. So we don't substitute something into E until we're completely done with all of our calculations, okay? So now I want to show you on a graph a relationship here between E and some of these other functions, okay? So let's say we had y was equal to 2 to the x, okay? So I know it's going to go through this guy right here, and I'm going to just do estimating here on this, okay? So let's say this is y is equal 2 to the x, all right? If I had y is equal to 3 to the x, now let's think about that. My base is bigger. I know it x is equal to 1, y is 2, x is equal to 1, y is 3. So this guy is going to be above the y equal 2x. On the right-hand side of the y-axis, it's still going to go through, right? And it's also going to come down, and it's going to approach the x-axis faster than the y is equal to 2x curve would, okay? So what would you expect then from y is equal e to the x to look like? Now, remember what we said a while ago. E is approximately 2.718 dot, dot, dot. Well, that is between the 2 and the 3, so we could expect our E function to look just like this. It would be in between the 2 to the x and the 3 to the x functions as we're drawing them, okay? So it's something you're going to be dealing with as you get into more study in your other courses and things, okay? But the important thing is it's just another graph. It has characteristics that we talked about. It's always positive. It does not intersect with the x-axis or go below it. Constantly changing, okay? This x-axis is an asymptote. It approaches it, it gets closer and closer. Now, how can we say that it never reaches it? Well, the example I always like to use, if I approach something and I move one step closer to it, and I've calculated this distance, and I says, ooh, this is as close as I can get. Well, I could actually, take half of that distance and get a little bit closer. So that's how a process of an asymptote works. No matter how close I get, how small the distance is between the function and your asymptote, I can always cut that distance in half again, half again, half again. Ridiculously small numbers, it'll look like zero way out here, but it won't ever get there, okay? So we talked about how this function always passes through 0, 1 and 1, b, where b is my base. We talked about what happens to the graph when I make my base less than 1 and greater than 0, right? So what have I said here? My base is a fraction, right? So they're all going to have this shape where the increase is left of the y-axis. The right side of the y-axis is where the x-axis acts as an asymptote. Then we talked about this natural number. I'm introducing it because you're going to be using it. Now, this formula here is how to calculate it. We are just going to use the representation of E in our equations, okay? We're not going to be calculating it out for a value of N. And then we talked about this relationship between functions so that the larger the base, the steeper my change occurs. Now notice, the larger my base, the closer this curve is to the y-axis, right? The bigger my base, the faster my function approaches the x-axis as an asymptote. And then we just showed the relationship between a base of 2, a base of 3, and a base of the natural number, okay? So those are the things that we want to talk about with exponential functions, and next time we're going to get farther into working with those. So that concludes this lesson on exponential functions, and I will see you guys next time.